Okay, let us continue the third part of today's class. Okay, let us continue to look at this algorithm. Okay, line 5, for all I is equal to 1 to capital N, okay, where capital N is the number of secondary users, do the following works. Okay, line 6, update the states and costs according to equations 2.8 to 2.10. Okay, let us see equation 2.8 first. Okay, equation 2.8, IIT is equal to 0. Okay, if gamma ITS is greater than or equal to gamma I. Okay, where gamma ITS is given in equation 2.2. Okay, let us go to equation 2.2. Okay, in equation 2.2, gamma IS is the corresponding SINR for secondary user I and can be computed by this equation. And gamma IS must be greater than or equal to gamma I. Okay, and gamma I is secondary user I's required SINR threshold determined from quality of service QoS goals. Okay, let us go back to equation 2.8. Excuse me. Okay, and LT is equal to 0 if gamma 0 TP is greater than or equal to gamma 0. Okay, where gamma 0 TP is the SINR of the primary user at time t. Okay, and gamma 0 TP is given in equation 2.1. Okay, let us go to equation 2.1. Okay, this is the signal to interference plus noise ratio SINR of the primary user, which is expected to satisfy the following condition. Okay, gamma 0P can be computed using this equation, which is greater than or equal to gamma 0. Okay, and gamma 0 is the primary user's required SINR threshold as determined from the underlay DSA. Okay, DSA means dynamic spectrum axis configuration. Okay, let us go back to equation 2.9. Okay. Okay, and LT is equal to 1 otherwise. Okay, next let us see equation 2.10. Okay, we define the cost function of secondary user I, okay, by equation 2.7. Okay, equation 2.7 is this equation. Okay, DI is the end-to-end distortion of secondary user I, and PS is the vector which contains P1S to PNS, where P1S is the transmit power of the first secondary user, and PNS is the transmit power of the nth secondary user N, and RIS is the channel coding rate of secondary user I. So the end-to-end distortion can be written, can be expressed as this function. Okay, let us go back to equation 2.10. Okay, so by equation 2.7, we define the cost function of SU, secondary user I, at time instance t as follows. Okay, small cit is the cost function of secondary user I at time instance t, which is equal to capital C. Okay, where capital C is an arbitrarily large constant, larger than the maximum possible variable for DIT. Okay, where DIT is the end-to-end distortion of secondary user I at time instance t, and DIT is a function of PITS and RITS. Okay, where PITS is the transmit power of secondary user I at time instance t, and RITS, okay, do you remember what is RITS? Okay, let us go back to review it. Excuse me. Okay, RITS. Okay, here is the RIS. It is a fixed channel coding rate. So RITS. Okay, let us go back to the page of equation. Okay, 2.10. So RITS is the channel fixed channel coding rate of secondary user I at time instance t, indicating a failure for a secondary transmission to meet the target SINR, or the violation of the dynamic spectrum access rule for the primary user. Okay, so small CIT, that is the cost function, is equal to a large constant C, capital C, if LT plus IIT is greater than 0. Okay, where LT is defined in equation 2.9 and IIT is defined in equation 2.8. Okay, and small CIT is equal to DIT of PITS, RITS otherwise. Okay, let us go back to the algorithm 1. Okay, so line 7, update the Q value QIT plus 1 of SIAIT according to equation 2.13. Okay, so QIT plus 1 is the Q value of secondary user I at time instance t plus 1. It is a function of SI. Okay, SI is the state of secondary user I, and function of AIT, where AIT is the action taken by secondary user I at time instance t. Okay, and let us see equation 2.13. Okay, in equation 2.13, okay, we have explained it in the earlier time of today's class. Okay, it is the equation to update the Q values with the iterative scheme of state action value backups as follows. Okay, so from this equation we can get QIT plus 1 of SIAIT. Okay, let us go back to algorithm 1. Okay, so line 8 is end 4, that is end the 4 loops of line 5 to line 8, And in line 9, t, the value of t is changed to t plus 1. Okay, that is t is equal to t plus 1. Oh, sorry, we must say t is assigned to a new value t plus 1. And line 10 ends the while loop, okay, from line 1 to line 10. Okay, this is all about algorithm 1. Okay, next page. Okay, it is worth noting that the standard of policy. Okay, what is the meaning of policy? Let us see the handout. Okay. Excuse me. Okay, page 44, problem 1. What is of policy? Solution: an of policy, whereas is independent of the agent's actions. It figures out the optimal policy regardless of the agent's motivation. For example, Q-learning is an off-policy learner. Okay, let us go back to the slides. So, off-policy Q-learning algorithm has an exponential time complexity. Okay, so what is this mean? Exponential time complexity. Okay, it means that the complexity of the off-policy Q-learning algorithm in the time domain is an exponential function of the size of the input of the algorithm. Okay, if you have learning algorithm, okay, if you have taken the course about algorithm or complexity, okay, you should know what this mean. What does it mean? Okay, therefore, algorithm 1. Okay, let us see algorithm 1 again. Okay, it is this algorithm. Basic strategy learning based on standard Q-learning. Okay, it is a 10-line algorithm. Okay, and I have explained it before. Okay, therefore, algorithm 1 is only computationally tractable when the state action space of each secondary user is sufficient small. Okay. Consider that by ignoring the interaction between secondary users and assuming the underlying state transitions of the secondary users are stationary. Okay, what is the meaning of this sentence? Okay, let us see the handout. Okay, problem 2. Assuming the underlying state transitions of the secondary users are stationary. Okay, what is the meaning of this sentence? Okay, to understand the meaning of this sentence, we must to know what is the meaning of this keyword, stationary. Okay, solution: a discrete time stochastic process. Okay, what is a stochastic process? Okay, if you do not know it, you should take the course stochastic process, which is provided by the Institute of Communications Engineering. Okay, xn, where n is greater than or equal to 0, is stationary if for any time points I1 to In and any m which is greater than or equal to 0, the joint distribution of xi1 to xin is the same as the joint distribution of xi1 plus m to xin plus m. Okay, so we can know that first xn is a random variable. So here are n random variables, and here are also n random variables. Okay, so we can know that this means the joint distribution of these n random variables at any time points I1 to In is the same as the joint distribution of these n random variables. Okay, so the joint distribution does not depend on the time shift m. Okay, so in other words, the joint distribution is time invariant. Okay, so we know that the we have known the meaning of stationary. Okay, so what is the underlying state transitions of the secondary users? Okay, in our case, the secondary users can be modeled as a Markov chain. Okay, so there is an underlying state transitions of the secondary users. Okay, so the Markov chain, okay, we know that a Markov chain is a discrete time stochastic process in our case. Okay, so this is the meaning of assuming the underlying state transitions of the secondary users are stationary. Okay, let us go back to the slides. Okay, the basic individual learning scheme in algorithm 1. Okay, let us see algorithm 1. Okay, algorithm 1 is the basic strategy learning based on standard Q-learning. Okay, it is a 10-line algorithm. Okay, we have explained earlier in today's class. Okay, let us go back to page 44. Only provides an approximated process of optimal strategy searching. Okay. Moreover, a course. Okay, what is course? Let us see the handout. Okay, page 45, problem 1. What is coarse? Solution: rough and not smooth or soft, or not in very small pieces. Okay, let us go back to the slides. Okay, a coarse discrete state action space with actions represented in relatively small sets may severely undermine. What is the meaning of undermine? Okay, let us see the handout. Okay. Okay, problem 2. What is undermine? Okay, solution: to make someone less confident, less powerful, or less likely to succeed, or to make something weaker, often gradually. Okay, let us go back to the slides. Okay, undermine the representativeness. Okay, what is the meaning of this long word, representativeness? Okay, let us go back to, let us look at the handout. Problem 3, what is representativeness? Solution, the noun of representative. Okay, then problem 4. What is representative? Okay, solution. Typical of or the same as others in a larger group of people or things. Okay, let us go back to the slides. Excuse me. Okay, representativeness of the considered model for optimal strategy searching. Okay, as a result, the use of Q-learning faces the challenge that large state or action spaces lead to long convergence times. This is already a challenge in many wireless resource allocation scenarios, but could become exacerbated. Okay, what is the meaning of this word? Okay, let us see the handout. Okay, problem 5. What is exacerbate? Okay, solution: to make something that is already bad even worse. Okay, let us go back to the slides. Okay, exacerbated in cross-layer approach due to states and actions depending on more variables. This issue will be revisited over the following sections of this chapter. Okay, so we have finished teaching section 2.1. Do you have any questions? Okay, if you have any questions, please contact me. Okay, you can use email, and I will answer your questions at my earliest convenience. Okay, next we are going to look at the deep Q-learning and resource allocation. Okay, this is section 2.2. Okay, we now expand the ongoing. What is the meaning of this word, ongoing? Okay, let us see the handout. Okay, page 47, problem 1. What is ongoing? Solution: continuing to exist or develop or happening at the present moment. It should be present moment. Okay, let us go back to the slides. Excuse me. Okay, we now expand the ongoing discussion on resource allocation along multiple dimensions. The first such dimension follows on the note at the end of the previous section, where we said that a challenge encountered with Q-learning is the long convergence time. With a table-based algorithm referred to this way because it estimates the Q values for each possible pair. SIAI. Okay, I forget to tell you. Okay, we have explained what is the meaning of deep Q-learning. Okay, if you forget it, please review the handout of chapter 2. Okay, the pair SI and AI, where SI is the state of secondary user I, and AI is the action taken by secondary user I, such as algorithm 1. Okay, let us go to algorithm 1. Okay, in algorithm 1, it is a basic strategy. Okay, it is 25 minutes. See you next time. Goodbye.